Perceptual rasterization for head-mounted display image synthesis. We match rasterization of a virtual 3D world into a 2D image and its visual perception on a head-mounted display. Consider those rays forming a primitive. Cortical magnification theory explains that the fovea is seen in sharper focus because it is represented in a larger cortical area. Our foveated rasterization directly renders into such domain. This is enabled by tight and efficiently computable ray primitive bounds. A similar perceptual problem is latency, where the 3D world changes during rendering and the display interval. We introduce time fovea bounds that enable rasterizing rolling images where simulation time changes spatially across the image. We will now show consecutively foveated, rolling, and joint rasterization, starting with foveated rasterization. When rendering an image to a display, we would like to produce the highest image quality in the foveal region, now shown zoomed to the right and marked as a circle. This can be achieved by sending more rays, but is difficult in rasterization. As a solution, we propose to directly rasterize into the cortical domain, shown left, where important areas are larger. We now change the foveation, enlarging the foveal area in the cortical domain and improving shading in the display domain. This is an individual primitive in this domain for a simplistic scene, and here are its bounds. Now we compare foveated, non-foveated rendering and a 4x4 super-sampled reference. Foveal insets are on top. Note how the quality is similar to the reference, while compute time is similar to non-foveated rendering. A rendering of a flower, again, the reference on the right, common rasterization to the left, and our foveated rasterization in the center. Here, shading with a single screen space ambient occlusion sample. Note how our fovea appears similar to the reference, while noise is clearly visible in common and in the periphery of ours. This complex model is prone to geometric aliasing. Our approach resolves both shading and geometry in the fovea to a level similar to 4x4 supersampling. Our perceptual studies validate the approach using real eye tracking equipment. Here we show a recording of perceptual rasterization using real gaze data. Let's look at rolling rasterization for latency compensation. In this scene, a box undergoes motion during the shutter interval. Note how edges that are straight in the 3D model appear curved. We now show the bounds in a dithered overlay. Now the bounds for a similar primitive. This helicopter undergoes motion during the shutter interval. Here we compare common rasterization on the top, warping on the left, and our result on the right. Warping has difficulties resolving disocclusions while we directly produce a warped image. A scene made of a few large polygons is a stress test for rolling rasterization. Note how the ground plane is a single polygon, properly clipped against the rolling frustum. While large polygons can be difficult to handle, many small primitives pose challenges to vertex processing speed. We see that this 1.4 million polygon mesh can still be rasterized at real-time rates. The mesh is not watertight from simplification, leading to pixel dropout holes both in the reference and ours. Again, comparison between common rasterization, warping, and our approach. Finally, we combine foveated and rolling rasterization. First, we see common rasterization and a reference. Now we enable foveation in the center. Quality starts to become similar to the reference. When enabling only rolling, the image is deformed as expected, resulting in low latency, but image quality deteriorated again. Our joint approach provides both low latency and high image quality. Thank you.